Hi, this is Mr. Aber, and this is the video lesson on normal distributions. So what we're familiar with right now is a histogram, like this one, that illustrates the IQs of 1,000 imaginary people. And you know that in a histogram, the x-axis tells you the ranges of scores. So for instance, this stripe here is the range of scores between 100 and 105, and then on the y-axis, it's the number of individuals that fell into that range. So for instance, about 140 individuals had that score out of this imaginary sample of people. To understand a normal distribution, what that is, you kind of want to look at a histogram compared with this, a probability density function. Now this curve and the area under it are supposed to sort of represent the likelihood of a person falling into a certain range. So for instance, the likelihood that a person would fall in the range of 95 to 100 is about that stripe, right? That kind of means that you would expect approximately 130 people to fall into that range. And so on and so forth. You would expect approximately 80 people to fall into this range. And you would expect approximately 40 people to fall into this range. So when we look at the actual histogram with the probability density function, they do look very similar. But the histogram has, some spikes that go off the line of this curve, and they have some that come not quite up to where the line of the curve is, right? Because real data, generally speaking, doesn't match this perfect idea of a bell-shaped curve. And that phrase bell-shaped curve is, or just bell curve, is another way of saying a probability density function, or a normal distribution. The concept is, normally, if you had an infinite number of people, their samples would be distributed in this way, in this perfect curved way. So here's an illustration of a bell curve. This is a population of individuals, and you'll notice that it's sort of abstract in that it's not telling you how many individuals on this line, but you still get that idea. And underneath, we're representing standard deviations. So this line represents the mean. And one standard deviation from the mean is here, or here. And these sort of stripes represent percentages of the population that fit within this range. So you might say that from the mean to half a standard deviation from the mean contains 19.1% of the population. Realize that this is called a normal distribution for a reason, right? It's normal in that it is in a bell shape, and you have the same percentages falling either direction. If you had a large enough sample of a certain kind of data, for instance IQ scores or weights of people ages 15 to 19, or certain other data, it would actually closely match a normal distribution. Some types of data sets do. So we find this normal distribution to be a valuable tool for analyzing things. For instance, if you're looking at IQ scores and you fall within this range of above 1.5 standard deviations from the mean, then you might say that you have a high IQ. And if you are age 15 to 19 and you fall into this range of weight, you might say that you are significantly smaller than most people your age. It's a tool for analyzing the characteristics of a whole population. Also realize these add up, right? So like above 1.5 standard deviations from the mean doesn't just contain 4.4% of the population, it also contains this 1.7% and this 0.5% and this 0.1%. And another way to look at this is to say if you take a random person, then that random person has a 15% chance of falling within this range and a 4.4% chance of falling within this range, and a 9.2 plus 4.4% of chance of falling within this range. So this is just a tool for analyzing data if you already know the characteristics of that data. And that is what a bell curve, a normal distribution, a probability density function all mean. They mean this kind of tool for analyzing a data that actually closely matches the bell-shaped curve when you graph it.